Does it mean they don't share something? Absolutely not. They absolutely share something. That I have another question on.
Okay. So the homework I handed out was just I had two mistakes on there and I corrected the two mistakes and it's the same homework. It's nothing new. You will be getting another homework shortly, and our exam is going to be today. Right now, no, it's not going to be today. And it'll not be next week either. It's going to be the week after that. So, so it's not next week. It'll be the week after that. And I'll explain next week what I do with the exam and stuff like that. For those of you who have had it, you already know what I do. But okay, okay. So that said, let's see. I need my little barrier here. Okay. So we're talking about the classical partition function. Okay, so remember what we had before. So what was our partition function that we had at the beginning?
Sum of all states.
Just call it sum on I.
E
to the
minus
beta EI. And this I was a sum over
all possible marker states.
all the possible marker states. And in general, what does that mean? It really means that we're going to sum over all the various quantum numbers on the system. So this is a sum over all possible microstates. And it usually means summing over all the quantum mechanics, all the quantum numbers of the system. So typically what it means is summing on all possible quantum numbers for each part. Okay, well, what did Boltzmann not have? Quantum mechanics. So the question is, what did Boltzmann do? So we said if you're a Boltzmann, and what was your energy back in the 1800s? Kinetic plus potential. Okay, so your energy here is so classically. And I'm just going to take one particle. What's going to happen here? This is going to be your kinetic, and for the rest of your life, kinetic is always T. Okay. Potential for the rest of your life is always going to be V. Like this. And so kinetic for one particle is going to be 1/2 mv squared plus v. Okay. This v is a little v, so it is the velocity. Now we do something more. We don't leave it as 1/2 mv squared. What do? We multiply the top and bottom by the mass, and we write this, right? So we do this. And then your mass times velocity is your linear momentum. So this is your linear momentum squared over 2m plus your potential. That's what we had classically. So now if you're Boltzmann, what do you have to sum over then?
All the possible momentum.
All the possible momentum. And this momentum is a vector. So what does that mean? You have to sum over all possible
X, Y.
X momentum, Y momentum, Z momentum. Your potential energy depends on position, so you have to sum over
position.
all the X, all the Y, all the Z. That's what you'd have to do classically. So what Boltzmann had, we had a sum on dpx, an integral on dpx, dpy, dpz. Okay. Sum over dx, dy, dz, and e to the minus is beta p squared over 2m plus v like that. That's what Boltzmann had. So for one particle, how many integrals you end up with? You end up with a 6-dimensional integral. Okay, this is way, way, way too hard to write. So that's going to become for the rest of our life. Yeah, just one integral, but that one integral represents 3 integrals. You're going to say d3p. Okay. The 3 just means that you have 3 like that. Okay. And what does then this? Okay. What does that mean? Yeah, this is going to be d3r. Okay. Now, often R is called Q. Okay, so often called Q.
Is that its middle name?
Yes, and it had a little name. It's like, my baloney has a first name. Too young for that. Okay, so it's often called Q. And there's a reason for this. And so what we're summing is over all the positions and all the momentum. And when you sum over all the positions and all the momentum, you call that space phase space. So the space of all possible P and R, I'll say /Q values, is called phase space.
What do you mean by space? Like a vector space of all these?
Just in other words, if I had like a graph of X, Y, Z, I'd be something overall here.
Yeah.
So now what I'd have it on X, Y, Z,
And
and then on here, then I'd have another 3 dimensions, which you can't do. Then I have PX, PY, PZ, and all that would be phase space.
okay.
Okay.
So like one part of one state, microstate is a point in that phase space.
Classically. Yeah. Does that make sense? Now we had a little complication here. Is that what are the units for this Z up here? It was dimensionless. Okay. So this is dimensionless up here. This Z is dimensionless. The problem with it is that this Z is not dimensionless. And so we need to divide by something that has units of length times the momentum cubed. And so what did we say as units of length times momentum? H. Yeah, so we said that Planck's constant. H has units of, and again, I always put brackets around things for units. Okay. This has units of length times momentum. Okay. And so what we do to make this dimensionless, we divide this by 1 over h cubed to make it dimensionless. So what we do, we put this 1 over h cubed vector here. Okay. That makes sense? So that's our classical partition. Questions? So we took one case last time. We took the case of one particle. If you have one particle, what's your potential energy for one particle? 0. Okay, so we did this crazy case.
Because it was by itself or 0 because
It's 0 because it's by itself. And in the box, there's no potential in the box. So if I put you in a box all by yourself, you'd have no potential. And just worried about dominant potential, you wouldn't have it. It's in a box by himself. Okay? It's only when you interact that you can have potential.
That's why
Wow.
they put 2 prisoners in one cell.
Exactly. So there's potential. Okay? It makes so much more sense now. I've heard of 2 prisoners in a cell. I always think of the prisoners so long. It's profound green game theory. You've never heard, what's the prisoner's dilemma?
There are 2 people, they're in their own separate rooms, they can't talk to each other. An investigator comes into the room and says to both of them separately, you have a decision, you can either rat out your fellow person or you could stay silent. I've given the same option to your fellow person.
Well, rat out the person and go free.
Oh, yeah, rat out the person, go free, sorry.
Or you can basically,
Stay silent, but you have to depend on the other person to not rat you out.
okay, the question is, what do you do? Okay, so the question is a profound game theory. So, and then basically turns out if they cooperate, then it ends up being, if you look at expectation values, that ends up being better for everyone. But
If you cooperate,
if you don't,
oh,
that you basically, if you cooperate with each other, then it turns out, you're not gonna rat each other out, it turns out to be all overall better. Okay, that's not related to the, but if you're ever in that situation, you could just think this is prisoner's dilemma.
I'm staying quiet.
Exactly.
Unless you don't trust the other.
So let's take, we're doing an example here for one particle. In a box. A volume this V is the volume box, okay? This V is the potential, okay? And then this little v here is velocity. So,
Just to make it.
Two of them are gone.
what?
Luckily for us, two of them are gone.
Exactly. So what happens into our Z here? So our Z becomes what? It becomes, let's put it here. V becomes this 1 over h cubed, this dpx, this right is d3 like this. Here, e to the minus beta p squared over 2m, and then I have this integral limit of d3r, e to the minus beta, and then it's 0 here. Because there's no potential. So I split this up into two pieces like that. Okay, does that make sense? This is 1, and what happens then if I integrate d3r over all space? You get the volume. So this is just your volume. So this gives me z equals 1 over h cubed. Here. And then what did we do with this? Last time we said that we could write this as dpx, dpy, dpz, e to the minus beta over 2m. And what's another way of writing p squared? Since it's a vector,
px squared.
px squared plus py squared plus pz squared. This is a vector. And then we said we could then rearrange that one more time. So I can write this as b over h cubed, z. This will factor into a dpx, e to the minus beta over 2m px squared. And that gets multiplied by this fellow here. It's multiplied by the last time. Everyone happy for that? Then what did we say? Okay, all these integrals are going from minus infinity to infinity because you have to integrate over all possible momentum. And what do you notice about each of those integrals?
They look the same.
They're all identical. So all we have to do is work it out once and then cube it. They're all identical things. So this is really v over h cubed, the cube of minus infinity to infinity, not dpx, e to the minus beta, px squared over 2. We did one more thing. What did we say a mathematician would call this function here?
An even function.
We call it even. And if I have an even function going from minus infinity to infinity, you can always write that as
Twice the integral from 0 to infinity.
exactly. So that led us to is the following. Our whole thing reduced to z equals v over h cubed 2 times integral going from 0 to infinity of e to the px, e to the minus beta, px squared 2m, that whole thing is cubed. Okay, everyone happy with that? Then we did one more thing and then we called it good. We said, hey, looks like
Integral of e to the minus alpha x squared.
yes. Homework 1. Okay, we worked up this result here, where this ends up being, we had this guy. I said memorize that integral because it occurs all the time.
Half pi over alpha.
1/2 square root pi over alpha. So in this case here, what is our alpha?
Beta over 2m.
Beta over 2m. So this whole thing becomes v over h cubed. I'm going to take out the 2 cubed here. Times 1/2 square root pi over beta over never after that. I wrote the beta as KBT last time, I'm going to KBT up here. Okay. This right here. How is that guy? I'll put that down here. I have my beta in the bottom and my 2m come up the top. Okay. And I can kill the factors of 2. B over h cubed times basically 3/2 power of pi 2m beta. So that's where we left things off last time. Any questions on that? Okay. Now we want to find the average energy of this. Well, what's still going to happen here? This is still going to be over I. Yeah. I mean, that's always true. That's always true. But what else is it equal? Minus partial of the natural log of z with respect to beta. Okay. That makes sense? So let's actually do this. We're going to get a profound result. We get minus partial with respect to beta. Okay, if I take the natural log of this, let's put it in here. Okay. What would I do first? Well, I would do the log of all this crap here. Okay, and I would try to get the beta all by itself. We're going to use the properties of logs. Okay. So what does this equal then?
ln of like v over h.
Okay, so let's get rid of this crap. So this is the ln of v over h cubed plus. Okay, so then I can say then the logarithm of this guy here, what can I do with the 3/2? I'm going to put out in front. So then this is 3/2 times the log of pi to beta 2m over beta. And I still want to be lazy. Can do anything with my friend here?
Yes, you can just move that again, like keep the 2 pi m in there and minus 3/2 ln beta.
Yeah, this is basically some quantity over another quantity. I'm taking the logarithm. This is going to be the logarithm of the top minus the logarithm of the bottom. Okay. It gives me the log of v over h cubed plus 3/2 the log of pi to m minus. And again, you don't have to do this. You can just take the, it's just, again, I like being lazy. Is everyone happy with how I did that? Good. Okay, now why is this really nice to take the derivative? Just like beta.
Bunch of stuff is constant.
Hey, this one is
0.
0. This one is 0. What is the logarithm of this one here? So what am I get left with? I'm left with u equals minus. I get the log of this guy. So it's going to be minus 3/2. What's the logarithm of beta with respect to beta? Yeah, so it's going to be 1 over beta. So that's how much beta result. Sorry. Okay, but what is my friend beta?
1 over kbt.
1 over kbt. So we get the result that probably everyone in this room knew. This. That if I have one molecule, one particle, at a volume V, at temperature T, the energy for that is 3/2 kBT. Where did the 3 come from?
Degrees of
Very
freedom.
good.
Yeah, yeah, the three, it's the same thing, right? We were integrating over PX, PY, and PZ, so
And
those
all those contributions were
the same.
the same. So this right here, this three. That three. The three comes from the integral of this dpx stuff equaling the integral, this dpy stuff. So if I were in only infinite Blackboard space, I wouldn't have to be doing this. And I can also see what the sign market is. But the important thing is that they will basically not run out of room for their sociology equations and political science equations. That's the good news. Okay. Okay, so that's where that three is coming from. The fact that each of these integrals are the same here. So if I wanted to, I could actually write this in kind of a stupid fashion. I could say that this 3/2 kpt is really 1/2 kpt. And this is going to be the integral from that, the dpx part, plus 1/2 kbt, and this would be the result from that integral dpy part. And then plus 1/2 kbt, this integral dpz. Okay. And that's the famous result. So what is this? This is really your kinetic energy for the x direction, kinetic energy for the y motion, then the kinetic energy for the z motion. This is nothing but, what is the grand name for this?
Equal partition of energy.
The equal partition of energy theorem. So this is an example of the equal partition. G. So I want to say what that is, because actually it turns out that there's some words here that we're going to need when we get to Phillips constraint theory, which will be after break. So equal partition energy theorem states that for each degree of freedom, and I haven't defined that yet, although probably most of you already know that. For each degree of freedom, for a particle, there is an average kinetic energy 1/2 kV. So basically it says that for each degree of freedom, which I'm just going to call it EOF, average kinetic energy now that begs the question, what on earth is the degree of freedom? When you turn 16, you can drive. That's the degree of freedom. Okay, meaning that this particle here is over 16 and over 21 because now it can drink. And it can also vote, so it's also over 18.
Okay.
So basically it means that
3 degrees.
particles are over 21.
Okay.
After 26, they can do car or rent a car.
Yes, exactly. I mean, then they have more degrees of freedom. Okay, freedom. Okay, so what's the degree of freedom? Let's say I have one part. My fist is going to be one particle. Okay. How many ways can this particle move? It can move this way, and then up. There are 3 ways that this, independent ways that this can move. So a degree of freedom is an independent motion of a particle. And the number of degrees of freedom is the number of independent ways that the particles can move. So degree of freedom is an independent motion of a particle. For one particle in 3D, there are 3 degrees of freedom for X, Y, Z motions. That's the degree of freedom. I want to do more with this because we're going to need this point later on. So what would happen if I would have 2 independent particles? How many degrees of freedom would there be for 2 independent particles? Yeah, what would they be?
Particle 1 movement along X, particle 2 movement along X, and for all those.
Yep. So I basically have it, I'd have an X1, Y1, Z1. That's for the first particle. So I'd have 3 here. And then I could have an X2, Y2, Z2. Then for the other one. Okay. So this would actually have 6 degrees of freedom.
So a system of 2 particles would have 6 degrees.
Exactly. So in a case like this, if this equal of energy theorem is true, turns out that it's not anymore. No, it turns out it is. Okay. What would be the energy then for this system?
6 halves kBT.
6 halves kBT or just 3 kBT. Okay. That makes sense. Now, suppose actually these 2 particles are connected by some massless rod. So they're no longer independent. What happens then?
Asking different questions. I don't understand.
Only one set of positional degrees of freedom.
I can't wait to find out. I hope it's cool. Okay. So what happens if particles 1 and 2 are connected by a massless rod fixed? How many degrees of freedom are there now?
Six still.
I can't wait to find out. Okay.
Question.
Sure.
That T right there.
This is kinetic energy T,
Okay.
not temperature T. That'd be T. Okay. Okay, that's okay. But this is kinetic energy T, so they're different. Okay, they don't equal each other. So, what would we have here? I'd have one particle here. I have an X, Y, Z, X1, Y1, Z1. I have another particle here, X2, Y2, Z2. And there's some sort of massless rod connecting the two. I'm going to say that this is L. Okay. What is this L given by? If I know the X, if I know the X, Y, and Z of one particle, the X, Y, Z of another particle, the length then would have to be what?
X1 minus X2 squared plus Y1 minus Y2 squared plus Z1 minus Z2 squared root.
Okay, so the square root of X1 minus X2 plus Y1 minus Y2 plus Z1 minus Z2. Okay, this is called constraint. Okay, so what did we say is the definition of a degree of freedom? It's the number of independent motions here. Okay, how many would, if we now have one constraint, how many degrees of freedom would we have? Right, now it goes down to 5. How come? Right, I can know x1, that's perfectly fine. I can know x2, that could be independent. I can know y1, that could be independent. Y2 could be independent. Z1 could be independent. Oops. Z2 cannot be independent. How come?
It's defined by one constraint.
Because this is fixed. And so therefore, since this is fixed, once you know all the other ones, one of them is actually predetermined. It's no longer independent. So now you would have 5 degrees of freedom. So in a case like this, what would be the average kinetic energy?
5 kBT.
It'd have to be 5 halves kBT.
But then they,
Does this have a name? Just give it the simple name. If this is oxygen and oxygen or nitrogen and nitrogen, just be a diatomic molecule. Okay, that would just be a standard diatomic molecule. So if I had one diatomic molecule, its average kinetic energy would be, I mean, where this is fixed here, okay?
Yeah.
That would have to be 5 halves kBT, according to this theorem. Okay, so what we have here is that the number of degrees of freedom would basically be 6 minus 1. So what you do is you take, in general, you have 5. So the average kinetic energy for this is going to be 5 halves. Okay. And we're going to prove that this is actually the case here. So if I imagine this is now a diatomic molecule, okay? What would be the degrees of freedom that you'd actually then use for a diatomic molecule?
you can move it around in X, Y, and Z.
Yeah, so I could actually look at the center mass of this. The center mass could do what way? It could move this way, it could move this way, and it could move this way. So it'd have 3 translational degrees of freedom. But what else could my little molecule do?
Rotate.
I could rotate like this, okay? That'd be another degree of freedom. I could rotate like this. And it seems like something's wrong. What else could it do?
Rotate
I could do
around,
this.
but that's the
Yeah,
same.
but
Okay.
that's
But it turns out that this one doesn't count, okay? And so what's going to happen is basically quantum mechanically what happens if you have something like this, and you rotate it like that, it's really the same as no rotation. And so what happens is if you have a diatomic molecule, there are 3 degrees of translation degrees of motion, and then there are 2 rotational degrees of motion. What's going to happen? That makes sense. We're going to prove that this is actually the case here. Does that make sense? Good. Turns out it doesn't. So we're going forward. Actually, no, I would try to explain it. If it could not. So in general, if I had n particles, what would be the total number of degrees of freedom I would have in the system? So in general, okay, I'll just say if we have n particles and NC constraints, the number of degrees of freedom is going to be what? Okay, so each particle would have what?
3 degrees.
3 degrees of freedom. I have n, so I'd have 3n. Then what would I have to do?
Subtract the number of constraints.
I have to subtract the number of constraints here. Okay, that makes sense.
Because like each of the constraints is an equation that defines a value of a variable based on code.
Exactly. Okay.
That's
Now, what we're going to do is that we're going to have eventually we're going to have something called the Phillips constraint theory. And so what Phillips is going to do, he's going to basically look at a imagine here's like some molecule like this. Okay. He's going to look at molecules like this. And imagine these are just balls with basically rods connecting the two like this.
That's how.
And so I can imagine a whole glassy network is basically being made up of a whole bunch of like, balls and little tubes connecting the two. And so what's going to happen here is that we can look at the total number of degrees of freedom. We can also then look at the number of constraints. And what he's going to ask later on, and this one occur until after break, he's going to ask the question, well, is there some condition we can look at when you're going to actually have a really good glass flow? So what would happen if we had basically, let's say we had a whole bunch of degrees of freedom, but we didn't have a lot of constraints. What could that system do?
Move around.
It could really slosh around a lot, quite a bit. If something could slosh around a lot, what could actually happen probably?
Can reach it.
It might actually be, maybe it could crystallize because it could come in some arrangement and then forms a crystal. So that could actually crystallize really quite easily. Well, suppose instead we had basically some degrees of freedom, but a ton of constraints, more than we knew what to do with. What would happen in that case? Yeah, there'd be so many constraints, you're very likely to have it crystallize.
Not like
Okay.
to have a crystal.
So, well, because there's so many constraints, it could easily crystallize. It's not going to easily form glass. Okay, because there could be so many constraints. Okay, you're not going to form glass either because there are just so many constraints. What do you think of baby bear solution? He's going to argue that actually the case for an ideal glass former is going to be basically you want to balance the number of constraints with basically the number of degrees of freedom. And so what we're going to do is look at that. And then later on, what we're going to do is we're going to say, well, suppose these constraints that we have here, maybe they set in at different temperatures. So maybe as you start cooling the system here, maybe these constraints, maybe they start actually forming at different temperatures. And so we're going to look at that, and that's going to become temperature constraint theory. We're going to look at, and that actually has worked out really well. Okay. So that'll be something we'll be looking at, right? But we actually need these ideas of degrees of freedom and stuff. Okay. So it's coming back. Now, with that said, suppose somebody doesn't believe this here. This 5 halves, this molecule, are you trying to tell me, well, what would this say here? According to the temperature constraint theory, how much kinetic energy would be connected with the rotation?
Yeah, two.
One kg.
Yeah, so what this is saying here. So equal rotation energy, that's just getting too far to the right. That's gonna be, it's true. Then this value here, we're saying this. It's really going to be 3 halves kBT here. This would be for the translation. Plus what? 2 times 1/2 kBT for the rotational. So let's actually go through and actually try to figure that out, if that's truly the case. Okay. Oh, true. That's the average kinetic energy for rotation. Or dihydrogen molecule. Is 2 times 1/2 kBT plus kBT. Okay. The question is, how do we do this?
We need to.
Okay, so I'm not gonna, let's pretend that the molecule isn't moving like this.
Yeah, we need to.
So it's just gonna have kind of rotational stuff. Hey, you all had first semester physics. What is the energy for a rotating object?
Depends on its angular momentum.
True. Let's start off by writing maybe T rotation. With Banner, I can go back and change your 125 grade.
Like IR squared or something like that.
Okay. I like the IR. Okay. Meaning the I part here. Okay. What is I?
The moment of inertia.
Moment of inertia. times angular velocity, the rate at which this thing rotates. It's omega squared. Okay, this is your angular velocity. Okay, consider that isn't there something like angular momentum in there? Yes. How do we get angular momentum in here?
What of inertia, it can be written in terms of angular momentum, it's like M
Okay.
times L.
Almost. Okay, I'm gonna multiply this top and bottom by something. What is it gonna be?
M over M.
I. So if I multiply the top and bottom here by I, you got I omega squared. Quantity squared over 2I. What is I times omega?
It's that angular momentum.
That's your angular momentum. So this is your angular momentum squared over 2I. Okay. So that's your gonna be the energy. Okay. Now I want to do this with the original partition function. Because probably I'm going to make this into one. I'm going to make this into another one for you. I have to make sure this goes. So let's go through and do calculate the energy using the sum on I value. So let's calculate the using. Plus it'll be you could redo using this. Okay. So we put that in here. We'll put a gap here. What you want is in that gap.
Maybe there's a degeneracy in angular.
We have that in here. Okay, I mentioned something before about angular momentum. A while ago. A lot of you have had quantum, a lot of you have had chemistry. So what do you know about L squared from quantum mechanics and chemistry?
Is equal to H bar square root of L times L plus one.
Yeah, this L squared is H bar squared. Okay. What is H bar?
You're asking the value?
Just
H over two.
that is where all the physicists hang out after work on Friday. The H bar. Here's the H bar. Okay, but it is always Planck's constant over 2 pi. Okay, times
L times L plus one.
L times L plus 1. Okay. Hey, but guess what? For a fixed L, right? So here's your L like this. Here's your L. We said we could actually look at the Z component of your angular momentum. Quantum mechanically, what did we? I did not prove it. That turned out to be involved in this course. What does your Z component of the angular momentum end up being?
H bar M square.
Good. So this right here is our M sub L times H bar, where
So it goes from
M sub L goes from where to where?
minus L to L, L to minus.
Yeah, from minus L to L or L to minus. I always start with a positive. I've been scared by minus signs, so I try to never make anything start with a minus sign. Okay. So it'd be L minus 1, all the way down to minus L. So what are we going to sum over here? We're going to sum over all L values. L going from 0 to infinity. But for any given value of L, how many states are there? Which would have the exact same value of energy?
There's 2L plus 1.
It's 2L plus 1 here. The number of states here. This value right here. This is the number of M sub L states that have same value. L. How does it prove that? What's the proof?
The proof of the fact that it's 2L plus 1.
Yeah. I just draw a picture, right?
Yeah, there's
So
L values
L,
above zero,
L
L
minus
values below
one,
zero.
L minus two, remember L's an integer. Then I have zero, and then I have 1, 0, minus 1, minus 2. To minus L minus 1, minus L. Right? So I'd have how many here?
L.
L. How many here? L. And then plus 1. I have 2 L plus 1.
But that only works if your L is an integer.
Correct. Well, I mean, this value here is,
Yeah, that's,
it works no matter, the number is always the same.
yeah, I'm saying it wouldn't work for spin.
It doesn't work for spin.
It's
That's
also two S
actually,
plus.
and that's actually one of the reasons why they ended up realizing that S had to be a fraction.
It does work for spin. It's still two S plus one.
Because that's actually how you ended up getting that the spin actually has to be a fraction. That's actually experimentally how they determine that. As the French say, oui.
But if like if
They have a word for everything, those crazy French.
yeah. But if the spin is 1/2, then there's only two states, not two values.
Correct. Okay, so what? Okay, aside, right? What happened here is that you basically had that. Okay, you basically had a beam of particles here. These are electrons. You basically had an inhomogeneous magnetic field here. That's an inhomogeneous magnetic field, and what happened? You basically, the beam came through here and it split like this. You had this state, you had that state. And they said, oh, spin is an angular momentum. It has to obey just like an angular momentum. So the number of these states here has to be then 2 times S plus 1. That's the number of states. Well, there's 2 here, and so this gives you S. That's actually where that comes from. It's from that.
Okay.
So it works in general.
Oh, yes.
Questions? Now, what are we going to do with this? Okay, I'm going to put this in. I'll put the L value up here. I think this is going to be a cliffhanger. Okay. I'm putting in the L value up here. That's putting it in here. Over 2I. And then there's a beta here. Beta like that. Okay, I'm going to multiply by 1. And how am I going to write 1?
And one fraction.
Yes. I'm going to write it as delta L. Delta L is going to be L plus 1 minus L, which is
1.
1. Okay, what's going to happen here? I'm going to take that sum and convert it to a integral.
You really do, but you do it.
That'll work. Well, we're doing the limit where this is works.
Where 1 is going to 0. That's an amazing move.
And then this then becomes 0. Hey, I think that's a friend here, right? This guy here is L squared plus L. What does 2L plus 1 look like?
A derivative.
The derivative of that. There we go.
This is e to the power of, or minus e.
This is going to be minus
E.
E. Let's put it over here. Minus E. This part comes along to the right.
Oh yeah, you want to put like the 2i over beta h bar squared in front.
What has to go in front?
2i over beta h bar squared.
2I over beta h bar squared. Evaluated from 0 to infinity. What does that equal? If I put in the infinity, e to the minus infinity is 0. If I put in 0, e to the 0 is 1. That's the lower limit. So this gives me 2I over beta. h bar squared. Okay, you tell me now how to get the energy from this.
We have to take minus natural log with respect to beta, minus partial with respect to beta of natural log.
Okay, I'm lazy. What am I doing with that? It's splitting the whole thing up. And write this as the log 2i h bar squared minus the log of beta. Okay. What does that give me?
KBT.
Oh, yell at me. No, this is, don't. This just gives me, right, this goes out, and I just get this one here, so this is u equals 1 over beta, which is KBT. We can write KBT as a half KBT
Plus a half.
plus a half KBT. We're doing sophisticated math here. What do we have? We recovered the equal partition of energy theorem per rotation. Okay. Hey, what else could our little molecule do? It could vibrate. If it vibrates, what would happen here? It'd have 1 degree of rotation for the vibration kinetic. What else do springs have?
Potential and kinetic.
Potential energy as well. So it's really going to have 2 other degrees of freedom, 1 for vibration kinetic, 1 for vibration potential. If only there was somebody who could work that out, maybe in homework 3, that might be assigned on Monday. Okay, that might be a really good thing. Okay, so what we'll do is you're going to work out that case for the next homework. Okay, have a great weekend.
Okay.